We started talking last day about forces. We said that a force is a push or a pull. Technically, Riley, a force is a lepton interaction between two. Well, there's a quantum definition. We're not going to go into that. If you're pushing on something, if you're pulling on something, we'll call that a force. We said that it was a vector, and so when I wrote symbol F, I really should have put the vector symbol over it, technically. Its units are newtons, named after Sir Isaac Newton, capital N. We talked about the idea of a net force or the combined force, and we used that as an illustration that, it does matter which direction you push on things. And a basic way we'll do it is we'll let one way be positive and the other way be negative, and we'll kind of go, bigger minus smaller or winner minus loser or something like that. Okay? We got one more? I told you that D is physics 12 when we start to go two-dimensional. Physics 12 in normal times is the first third is physics 11 done over again, but in 2 dimensions. If you take first year university physics, you'll find it's physics 12 done over again, but in 3 dimensions, because we live in a 3-dimensional world. And that, Riley, is really when you need calculus to handle most of the applications. Up until then, you can kind of work your way around with some clever workarounds, but
Could we please have the counselor come to the office, please? The counselor to the office, thank you.
We talked about Newton's laws. I said to you, I think I did my Aristotle little speech about how he had this whole life energy garbage, total garbage. Isaac Newton came along and said, I can explain how everything in the universe moves with 3 rules. The first rule we called, you got the notes okay? Yeah, find it and let me know, and then I can ignore you and continue on with my teaching, but I'm kind of watching, or give me a thumbs up, I'll get you a copy. He said that, look, objects don't naturally stop. If an object slows down and stops, fancy word, accelerates. I know it's decelerates, but we're just going to call that all acceleration, change in velocity. If an object has a change in velocity, there must be an unbalanced force acting on it. And if all the forces are balanced, it can't change its velocity, which means it's either going to stay at rest, if it was already at rest, or it's going to keep going in a straight line at a steady speed. It's typically phrased as objects at rest tend to remain at rest, objects in motion tend to remain in motion, which I always thought was kind of ugh. Are you accelerating? There's an unbalanced force. You're not accelerating? Forces are balanced. But it also works backwards. Are forces balanced? You're not accelerating. Are forces unbalanced? You must be accelerating. We're going to use Newton's first law to often figure out forces that are missing when we analyze a situation. We also called it the law of inertia. I introduced the concept of, I said we're going to treat mass and inertia as the same thing. The more mass an object has, the bigger a force you have to apply to get it to accelerate. Told you my car accident story, yes? I did, I can't remember who I picked. I think it was Aiden for the magician tablecloth trick. Yes, good. And we looked at the space station. We looked at the subway sleeper. I think I did Chris Angel's little magic trick to show you that force is a vector. We looked at a couple of situations already where we said we can analyze a situation. If we know an object isn't accelerating, the forces have to be balanced. So we said if we have 1,200 newtons down, we had to have 1,200 newtons up. Otherwise, it would be accelerating. And we got right to here, Newton's second law. Newton's second law is the equation. It's how you calculate force. And it's given as F equals ma, where the force and the acceleration are both vectors. F equals ma. It's on your formula sheet. You'll memorize this one because we're going to use it about 1,000 times in the next few lessons, and you'll get sick of looking it up. F equals what? F equals ma. Where m is the mass in kilograms, and a is the acceleration. Hey, did we just do a whole unit where we finished calculating acceleration? Okay, so there's going to be a lot of overlap, which is kind of nice. It also means that a Newton is actually a kilogram meter per second squared. Because if it's ma, and if m is in kilograms and a is in meters per second squared. In fact, we used to measure force in kilogram meters per second squared, but it was decided about 100 years ago, let's call that a Newton. And that way we can abbreviate and name the unit after him. You'll find a lot of the units that you learn that are named after scientists, you can actually break them down into their fundamental component subunits. There's one still that's really, really long. That one may get renamed in your lifetime. It may end up getting called an Einstein because there's no unit named after Albert Einstein, but we'll see. Hashtag nerd trivia. Example 4. Malcolm has a mass of 65 kilograms. What's the magnitude of the gravitational force acting on him? Huh? What's this asking me to find? The magnitude, the size of what? Gravitational what? F equals what? So the first thing I would write is this. F equals ma. Now, we're going to, if you haven't figured out, in physics, we tend to abbreviate and be organized. My abbrev for gravitational force is F with a little lowercase g. Fg is gravitational force. And we can figure this out. What's Malcolm's mass, according to this question, in kilograms? And, hey, we just learned this. What's the acceleration due to gravity? I'm not going to include the negative because it just asks for the magnitude, the size, so don't include a direction here. How many newtons of force is gravity pulling on this 65 kilogram person? I can do this in my head. It's going to be 650 take away 13. It's going to be 637. Double check me. Yeah? 637 what? Newtons. If you ask me to give a direction, because force is technically a vector, down. If I'm going to be really fussy, towards the center of the Earth, because Australia's down is our up, but whatever. Note, gravitational force has a special name. We call it weight. Weight is newtons, not kilograms. And I will be fussy on that, but we'll do a whole lesson on that later. So far, so good? F equals what? Ma. From that, we can start to see how mass affects acceleration, how mass affects force. Well, first of all, B. Malcolm stands on a table. I don't have Malcolm here, so, oh heck. Max, can you stand on that desk table behind you, please? Max's name begins with an M. He's going to be our Malcolm analog. Okay, see Max? Okay. What's the magnitude of the upwards force that the table exerts on Malcolm? Now, is he accelerating? So that means the forces must be, I'm looking for a word that starts with letter B, must be balanced. And so we're going to represent Malcolm with a dot. You'll get this in just a second. What are the forces acting on him? Get the obvious one, the one we just calculated in part A. Which way? So I'm going to do this, and I'm going to tell you that there's 637 newtons down. If that's all, it's impossible for Malcolm not to be accelerating newtons first. If that was it, he must be accelerating. Is he accelerating? So there has to be a force pointing which way? Exactly how big? 637 newtons. What's creating that force? Believe it or not, the table. And now that I've told you, can you feel it pushing up through your feet? It's always there. We ignore it all the time. You don't even notice it. But now that I've mentioned it, oh yeah, actually you're right. I feel something pushing up through my feet. Thanks, Max. You can come down from there. There has to be, and I'll call it F table, and that's got to be 637 newtons. It must be that. This is why I said to you, Kiana, Newton's first law is really handy to find missing forces. I know it must be there. Otherwise, he would be accelerating. He's not. We call a diagram like this, where you represent the mass with a dot and you label the forces with arrows, we call it a free body diagram, or FBD for short, and we'll do a whole lesson on them. That may be the single most useful tool that I give you in this unit. If the most useful tool in the last unit was DFIC, the most useful tool here is going to be, you're going to hear me say over and over, this is a job for a free body diagram. In fact, often, if you ask me a question, I'll look at your paper, and if I don't see a free body diagram, I'll walk away. Example 5. Is it turn the page or page over? Okay, please don't make me have to tell you that next time. I think this should be turned. No, but it is. Okay. The space shuttle has a mass of 2.03 times 10 to the 6 kilograms. It does, or it did when it operated. Any of you seen the space shuttle live, by the way? I got to California Science World has one of the old space. I think they have the Enterprise, so I got to see it live. It's pretty cool. If each engine can exert a force of 12.5, what's a capital M in front of a letter mean? Meganewtons? Okay. What's the maximum acceleration of the space shuttle? No, there are 2 engines. Alrighty. Kiana, what's this question asking me to find? The maximum what? You know what? Let's fall back on our... Peniel, have I written something down? Are you with me? Okay. Have I written something down? Do I feel better? Am I more relaxed? Okay. I don't see a VI. I don't see a... Well, let's list stuff that they gave me. Kiana, what's this 2... You're doing your glasses? Sorry. I'll go right next to you. What's this 2.03 times 10 to the 6th a measure of? What are the units next to it? Loud and proud? So what's it a measure of? What do I measure in kilograms? Starts with letter M. As soon as I write that, I'm thinking, I'll bet you there's an equation that has acceleration and mass in it. F equals what? That's what I'm thinking. As opposed to VF equals VI plus AT, or D equals VI, T plus F, A, T squared, or VF squared equals VI squared plus 2, A, D. Right away, my mind's going there. I bet you they gave me a force in newtons. Kiana, did they give me a force in newtons? What? How big? Okay, so 12.5. Mega is 10 to the... Thank you for being clever enough to know that it's on your green sheet. And then how many engines, Kiana? Okay. I'm looking for an equation that's got an A, an M, and an F in it. Annika, F equals what? Oh, except, Kiana, what am I trying to find? Get the A by itself. How would I move the M over? What's the M doing to the A? Adding some... So? Holy smokes, Mr. Duick, are you saying that you can give me a brand new equation and I can rewrite it without you actually having to teach me these skills now that I've learned this formula manipulation stick? Yes! So are you saying here's yet another equation for acceleration, Kiana? Say yes. Are you going to memorize it? Say no. Do you need to? You can derive it from F equals what, MA. Okay, so we're going to get 12.5 times 10 to the 6th times 2 all over 2.03 times 10 to the 6th, which is what? Ethan, can you actually pull that door completely shut? The other thing, if we don't, because of my weird wind pressure situation, that door will open and close like a ghost every time someone opens a door elsewhere, so it'll scare you. And I don't want you to be scared. Although on Halloween, that would be a great... Anyways, okay. What'd you get, George? 12.3? 12.2 or 12.3?
12.32.
12.3? If we go to 3 sig figs? Anybody else? Is that right? How many G's is that? How would you figure out how many G's that is? Go ahead. Divide by 9.8. Oh, it's acceleration, so meters per second squared. Yes, I checked my units. How many G's is that? More specific, please. You have a calculator. How many? Mr. Duick, I thought I read that astronauts pull like 5 or 6 Gs. I got 1.2 here. Are they lying? B, why does the maximum acceleration change as the engines burn? For astronauts, the Gs increase as the engines burn. Why? Momentum, we haven't talked about yet. That's a physics concept. You're technically right, but you're right without knowing that you're right. So I'm going to say wrong. Sorry, that was a weird answer. I know. Yeah. Because of inertia? Way to throw a physics word out there that you don't know what it means. Good try. Because of science? Yes, technically. So you ready? Kiana, we'll name this after Kiana. Kiana, what's your new acceleration equation? We'll call it Kiana's law. You derived it. Read it to me. So Kiana's law says this. Okay? Can you figure it out from that? As the space shuttle burns fuel, what happens to its mass? But the force stays the same. So as you divide by a smaller and smaller and smaller number, what happens to your answer? Do you know when the astronauts experience the biggest Gs? Right before they shut off the engines. Because the force thrust is staying the same, but they're at their minimum mass of, they keep some fuel for emergencies. That's why if you've ever watched a space shuttle or a rocket launch, it looks very slow and majestic at the beginning. It is. They're not pulling the Gs then. They're pulling the Gs later on as the mass of the rocket decreases, but the force hasn't changed because they're still revving the engines full. Does that make sense? I don't want to write a big paragraph. But does that make sense? So here's my version. As M decreases, A increases. Because of Kiana's law. We're naming it that for the rest of the year. A equals F over M. Nicholas, it turns out I can derive the momentum equation from that, which is why I said that you were sort of right without knowing you were right, but I don't know if you know what momentum is yet, so I'm talking forces still. Hey, how does Newton's second law, F equals ma, how does it explain why a sprinter might want to wear lightweight shoes? Yeah. Kiana's law again. Let's suppose you've worked out, you've lifted weights, you've maximized the force that your legs are capable of exerting. What else can you control in this equation? Yeah. Here's a product that I'm surprised hasn't been designed yet. To me, the ultimate would be to have some kind of liquid roll-on sole that you would roll onto the bottom of your foot. You would then stamp while it was still liquid on a specially designed tread mold that would give you the appropriate tread for that track, and that sticky mold would last for one race, but you'd have the whole upper portion of the shoe to me is wasted mass in my mind. So I'm a little surprised that no one has come up with a way to basically give runners, especially sprinters, where you don't need the shoe to last that long, and basically a roll-on or a glue-on sticky sole that only lasts for that race, and that you could customize to whatever. That would be minimal mass, especially in sprint, especially in the 100, when the difference between first place and sixth place is like 4/100ths of a second. Because I don't have the engineering or chemical skills. But if you go into engineering and you decide to enter sports science, try and make some money. Or it might be illegal. And maybe someone thought of it and it might be against the rules. There are a whole bunch of obscure rules in, track and field that someone has thought of. No, you can't do that. I'll give you an example where about 20 years ago, actually about 25 years ago, there was a backstroker who was a terrible backstroker, but a good physicist. And so he was the one, what he would start to do is he would dive into the water backwards and he would dolphin kick under the water because he'd run the numbers, and it turned out you're much more efficient under the water doing a dolphin kick than you are doing a backstroke. And so he would then surface about 10 meters ahead of everybody else on the first lap, and they would slowly catch up to him. He would do the turn, dolphin kick underwater, again gaining on them because he was faster under the water than they were on the top. They've made that illegal now, right? Now you can only dolphin, if you watch the Olympics, watch the backstroke, you can dolphin kick to a certain part, but there's actually a black line on the ceiling and down below, and you got to be above the water on the surface before you get to there. Newton's third, probably my favorite. Newton's third is typically phrased, for every action there is an equal and opposite reaction. Huh? I've never understood that. So Dan, here's what I have. You don't look at your phone, are you? No. Okay. Mr. Dewick says forces come in pairs. Technically, forces come in, if you want to, you can put the word opposite pairs. If you want me to write it algebraically, F of A on B equals F of B on A, but opposite. What would be a clever way to show opposite? Sure. In other words, a force has to be an interaction between two objects. If you put an object all by itself off in a corner of the universe, away from any planets, if there was nothing else touching it, it can't exert a force because it has to exert a force on something, and something has to exert a force on it because forces come in pairs. Let me give you some good examples here. I got to pause the video for a second. I got to stand up. So I've done my Newton's third rant. Oh, bathroom scale example. Yes. Pause. So how does Newton's third law help to explain why it's difficult to walk or drive on ice? First of all, Newton's first kicks in. You want to keep going in a straight line at a steady speed. To bring yourself to a stop, you need an unbalanced what? What causes that force normally when you're walking or driving? This is the force. We're going to do this whole day on it, but you introduced it already. Friction. Does ice have friction? Let's imagine when we're talking about ice, we're talking about perfect ice that has no friction whatsoever, okay? So, no friction, no stop. I don't want to write a big paragraph, so let me see how I would write that. I would say something like this. Car applies force to ice, but ice can't apply back. Can't apply the force back on the car. In which case, then, you can't get an unbalanced force. You're going to keep going at a straight line at a steady speed. Okay. What was your question? It's a good question. What about those rubber strings on like the tire or whatever? I think you need to be way more specific because I have no idea what we're talking about. So we're gonna spend an entire lesson looking at friction and what it's made up of, and in that lesson I can explain Kiana's comment about cleats or spikes, and I probably can explain yours. We'll look at how you can increase the force of friction, and you'll learn there's two main ways to do that. So can you hold that? And we'll get to that. I think that's lesson 3 or 4 of forces. Yeah, friction is a cool force. Put your pencils down, look up. How does Newton's third law help to explain why professional boxers need to wear boxing gloves? Forces come in. Okay, so I've had enough of Max's attitude. I'm going to hit him in the face. I'm not really going to. But if I apply a 500 Newton force to Max's face, what does Max's face do? Apply the same force back to my hand. And so one thing the glove does, it protects my hand. And then the other thing, F equals what? If I can accelerate a larger mass, bigger force. So you actually probably, I think, hit harder with a boxing glove than without a boxing glove. The force would certainly be larger if you can get it to the same speed. Okay? I don't want to write a big paragraph. Oh, how about this? F of hand on face equals negative F of face on hand. If I hit somebody hard enough to break a bone, I'll probably break a bone. Newton's third, forces come in pairs. So Newton's first, the law of inertia. If you're accelerating, there's an unbalanced force. If you're not accelerating, the forces must be, I'm looking for the begins letter B, balanced. Newton's second, F equals what? ma, and we have Keana's law, A equals F over m. Newton's third, forces come in opposite pairs. Why do you, turn the page, or next page over. Why do you lurch forward in a bus that suddenly slows? Which one of Newton's laws kicks in there? Okay. Why do you lurch backward when it picks up speed? And why are both of those technically wrong? Well, for the lurching forward, you sort of do. You keep going in a straight line at a steady speed. The lurching backward, actually, no, you're at rest, and when the bus accelerates, you just want to stay at rest. It's actually the bus is going forward from underneath your feet. Technically, you're not lurching backward. You're not going anywhere. But okay, we'll say lurching backwards. So what law applies here? Now, if you can't remember which one is Newton's first or second or third, if you simply said forces are balanced or the law of inertia, I will give you full credit. If you happen to know which one is which, you can certainly use that as an abbrev. So you can say Newton's first, and I'm good with that. But if you can't remember, is it Newton's first or second or third? Well, Mr. Dewick, the fact that it's at rest means it wants to remain at rest. I'd get that. Or the fact that it's moving, it wants to keep going at a straight line at steady speed. I'd get that. Example 2. Oh, we get to vote again. Once again, how high we hold our hand up is how sure we are of the answer. In this collision below, let's make it a big 5-ton moving van, and let's make the right-hand one a little Austin Mini. Okay? Which vehicle experiences the larger force? A, the truck, B, the car, or C, both the same? Let's think about this. Who says obviously the truck experiences the larger force? The truck. No one. Huh. The car experiences a bigger force, Mr. Dewitt, because the truck has a bigger mass. Car gets smooshed. Was that a hand? Did you do a little? No? You just doing a little stretch? Who says both the same? Really?
It's because you told us they come in pairs.
Which, by the way, is really counterintuitive to people who don't understand physics. If you had not had today's lesson, I'm willing to bet if I had asked at the beginning of the class, almost everybody would have picked B because it gets smooshed more. But no, it's the same. Why? You could say forces come in pairs. I'll give you full marks. I happen to know that that's Newton's third, so I'll say that. But you could also say forces come in pairs. So then here's the question. Why is it that the car and driver are almost always worse off as a result of this collision? Yeah.
There's more mass behind the truck, or more mass protecting it.
Hey, Kiana, what's your law? Smaller mass results in a large, from the same force, a smaller mass results in a bigger what? What does damage in a car accident is not the force, it's the acceleration. It's the acceleration. Which is why we typically don't put seatbelts on a bus. It's got a big enough mass that it won't decelerate that fast. Certainly we don't put them on a school bus because you don't pay taxes and you're not worth it.
That's what I always thought.
Yeah. We do now put seatbelts on like a Greyhound bus because those are adults that might sue the bus company. But for the most part, yeah. Sorry, but truth hurts, right? But for the most part, if you're in a really, really large, massive vehicle, you'll hardly decelerate at all. Like, we don't put seatbelts on trains, because if a train runs into something, it's going to go through that thing and hardly twitch. Okay? As M decreases, A increases. And what does damage in an accident is acceleration. Not your velocity, not your speed, not the distance. It's A. It's A. Not the force. It's A. Is that okay? What's your homework? You can work on this after you finish the test. We're going to take a short break, and then I'll do some quick Q&A, and we'll go on to the test. We'll take a bit of a break first. First of all, let's look at number 1. Number 1 says, little Nellie Newton wishes to be a gymnast. Hey, look at her. Is she accelerating?
No.
Then the forces must be, I'm looking for a word, okay. If she has a weight, a force of gravity of 300 newtons down, I'll let you see if you can fill in the blanks. I did attach the answers at the very, very bottom of that page, I think. Okay. Then we look at Burl the painter as well. It tells you what his weight and or scale. You can figure this one out. Can you then go to number 5? Okay. I put the answers typically in brackets, so you can try all of that first page. Number 5 is fair game. 6 is fair game. 7 is fair game. 8 is fair game. 9 is fair game. Number 10 is so easy that it's tough. This is asking, can you spot the action-reaction pair? The forces come in pairs. So you ready? 10A, head bumps ball. Forces come in pairs, so ball. That's all I want you to realize. And that's what you feel on your end, right? You don't feel your head hitting the ball. You feel the ball applying a reactive force back to you. So I'll let you try number 10 very quickly. Turn the page, please. 11, I have not talked about. I want to see who can have the, I know what they're getting at moment for number 11. I did put the answers there. Part 2. I don't want you to worry about F or G. Cross those out. Instead, number 1 is right here. I want you to classify these as examples of Newton's first or Newton's third, and you can just put a big 1 and a big 3. Some of these might have more than one answer. Here, I did not attach an answer key. We'll talk about this either later on in class or next class. So you can try 1, 2, 3, 4 is good. 5 is good. 6 is good. 7, 8, 9. Then we come to a little section on Newton's third. What's the reaction force to the action force in each of the following situations? If a player kicks the football with a force of 500 newtons up, the football applies a force on the player of direction?
Negative.
Down or negative, okay? So football pushes down with 500 newtons. That's what you feel through your foot when you kick it. You feel the football pushing back on you. Okay? So you can try all of number 1. You can skip number 2. Number 3 is good. In fact, you know what? Let's all look at number 3 for a second, the plate glass window. I don't know if you've watched movies lately, but it seems over the past 20 years or so that bad guys and plate glass windows are somehow magnetic. Here's what I mean. If it comes time for the bad guy to die, you'll know he's about to die because he's standing in front of what? A plate glass window, because they want that effect of the good guy pulling out the shotgun and blasting the bad guy off of his feet through the plate glass window. Now that's very good for drama. Why is that bad physics? If the bullet can apply a force to lift the bad guy off of his feet and throw him backwards, forces come in. That means the gun applied that force to the bullet as it left the barrel. The bullet would have applied that force. The good guy's got to be going flying backwards through the window behind him too. Yes? Yes? Okay, so you can cross out 3. We just did it. 4 is good. 5 is good. 6 is good. By the way, anybody here ever climb a rope? When you climb a rope, which way do you pull with your hands? Which way do you accelerate? So it's not your arms that make you go up. Right? Can't be. Just think. So it's 9:30. I'm going to say we're going to take a break till about 9:45-ish, and then we'll do some Q&A, and we'll move into the test. A couple of you aren't going to be writing the test. You'll just work on the homework.